For many of you have seen this, but for those who are new to this project we did, this is the first photo we got back from our CubeSat. With superimposed on that is a picture of the CubeSat, a little photoshopping. That was taken by a camera controlled in Spark Ada. The satellite was launched in 2013, almost 10 years ago. In November, it'll be 10 years. The way we got started on this was somebody with a lot of free time before that, a few years before that, posted this on their website at Aalborg University. And apparently with a free time on a rainy day, they had a little design of a 1U CubeSat. A 1U CubeSat is 10 by 10 by 10 centimeters, now 1 1/3 kilograms. It was 1 kilogram at the time. And looking at this, I looked and saw, well, obviously these propellant tanks down here look a little small to have something that could land on the moon. So I put together a spreadsheet trying to design in detail something and to see if it was possible to actually make something that could land on the moon in a 1U CubeSat, and it turned out it was. And I was an invited speaker to the Moon Society, the Space Development Conference in 2012, along with John Glenn and Scott Carpenter and Buzz Aldrin. Scott and Carpenter were just at the opening ceremony, which is a picture of me here in white tie and tails, one of the rare times I get to wear that living in the middle of Vermont. Glenn and Carpenter were just there for this opening reception, but Aldrin was there for the entire conference, and I had several conversations with him, and he was very interested in what we were doing in CubeSats. This is one of the designs I did initially, and this is a 2U CubeSat, basically just an enlarged version of the 1U that I had, with propellant tanks of the size that would make this viable. This was of such a size that if you put a 1U on top of it and deployed this in a geostationary transfer orbit for a communications satellite, it had enough delta V velocity increase to take it and a 1U CubeSat to the moon and put it in orbit around the moon. Here's an example of a 3U, 10 by 10 by 30. This bottom section here would fold out photovoltaic panels. It's not an optimum design, but it was a first attempt at making a look at this possibility. For actually landing on the moon, this is a commercially available thruster that would be capable of doing that. And you can get an idea of the size looking at a US penny here. It's just a few centimeters long. It's a half a Newton, and the specific impulse, which is a measure of the efficiency, 225 seconds. Here's an actual picture of the satellite before it was launched. There's a little tapped on tape over the lens of the camera to just keep it clean until we were ready to put it in the deployment box. GPS antenna here, photovoltaic panels on the CubeSat. Ours was just almost, it was 1,001 grams, so just over a kilogram. And it was put into orbit on November 19th, 2013. We completed 11,071 orbits, 475 million kilometers, equivalent to 3/4 of the distance of Jupiter. And ELaNa 4, with the educational launch of nano satellites, mission 4 was on an Air Force ORS-3 Minotaur 1 flight to a 500-kilometer altitude, 40.5-degree inclination. So it goes as far north as New York City and as far south as the Bass Strait between Australia and Tasmania. And it was in orbit for 2 years and 2 days. It's the only one of the 12 university satellites that operated until reentry. The last one quit 19 months earlier. There were 2 NASA satellites. Neither of one of those worked, and there were 15 Air Force satellites we don't know about. They were classified. We communicated with it the day before reentry, and the first successful university satellite from New England or New York, and until 5 years later, Brown University had one. There's a picture of our board where the camera was mounted here. There's our $20 camera, inertial measurement unit. The GPS antenna will be mounted here. It's not mounted yet. These are connectors that go to the side panels for both the photovoltaic output and the LEDs, which are on the panel. We put our Mad River Glen Ski If You Can ski area in small version at the ski area. They're in the bar. They have photographs of this bumper sticker all over the world, including one on the space station. But we have the distance record for the traveling 11,071 times around the Earth. Again, a picture just before deployment, a remove before flight pin, which keeps the power off. It's sitting on a couple of switches that you can't see here, which are deployment switches. And when you put in the deployment boxes, those switches turn off the power. And when they're deployed, the power then goes on. And we had a timing in there in our software to wait 45 minutes before deploying the antennas, which are in this bottom section of it, you can barely see here, to make sure that it didn't interfere with anything else. Here we're testing LEDs before putting the side panels on. And this is at the launch with my son, who's much younger than, he's now 18, and a student, Dan, who did about 80% of the software. My colleague Peter Chapin, who many of you are familiar with, supervised him and did the rest of the software and put together the software tools. I had chosen the technology to use Spark Ada, and just to show you the launch here. It's the rocket in the background. There it is. The bottom two stages are from a Minuteman II ballistic missile, and the top two. All the people commenting have CubeSats aboard. It was a night launch, pretty impressive. Solid fuel rockets do a nice show at night. And you get the roar of the rocket. We were about 5 kilometers from the launch platform, so it was fairly impressive. Yeah, they're talking about it went through a cloud. You still see it. I mean, we're getting ready for staging. It runs for a little over a minute in each of the first 2 stages. And you'll see a little flash with the staging. There it goes. Separated the stages. And that's as far as I'm going to show there. So here is the first picture again. The missing Malaysian airliners up here, if you can magnify this. And another picture taken from it. We had a lot of pictures of clouds. We got about 3 dozen really nice photographs from the mission. We would tell it that we called it a roll of film. It would take 36 sequential pictures. We didn't know exactly where it was when we told it to take pictures. It was just at a certain time. And we had lots of clouds. If it's pointing away from the Earth, which it is, the majority of the time it's just black. It doesn't have enough resolution to see the stars. Here's an idea of taking a 1U CubeSat and putting a ball of californium-251. It's the smallest quantity for critical mass of any fissile material. The problem is that's made in cyclotrons, so it's about $50 billion to get that, but surrounded by RDX explosive. This would be a nuclear explosion and would get rid of orbital debris in a large area, but no one seems to want to take us up on this idea. And so our software, we were the first group that was selected for launch when we applied it, but we weren't the first group launched because you put on different rockets and so on. And again, after 2 years and 2 days, it burned up. 8 others were never heard from at all. 2 had partial contact for a day. 1 worked for 4 months. Ours was heard from before it finished its first orbit with a handheld antenna in a parking lot at Wallops Island, where it was launched from. And so what we're now doing, in addition to the software that was developed for this, there was no operating system. It was on bare metal, as it is said. It was an MSP 430 TI processor for which there was no Ada compiler. And I came up with the idea of using Ada Magic, which is the front end of by Tucker Taft, the front end of Ada compiler, which puts out ANSI standard C as the intermediate language, and then using a standard C compiler, and that worked. I gave a presentation on this in Ada Europe in Venice, and then Peter Chapin put together all of the tools, and it actually works. So what we're now doing is we're continuing to add additional features to the software. And we have a system that's called CubedOS, as listed down here. It's available on GitHub. There are a couple of things that we're doing that might be ITAR controlled, and at the moment they can only be given to US users who would contact us for the rest of it. So one of the things, the spiral thrusting is probably something that is ITAR controlled. It allows you for 3-axis control with a 2-axis thruster, an algorithm that was developed at Jet Propulsion Lab. And our first master's degree student in software engineering, that was his project, and he implemented that. And we took it out and showed it to the people at JPL who were just ecstatic because they had developed this algorithm about 8 years before. Nobody had used it, and we had it working. So that was a very nice thing to show them. Then the next thing that we implemented, and this is still, it has a basic implementation, we're going to be improving it, is JT65. JT is Joe Taylor. He was one of my physics professors in grad school. He won this 1993 Nobel Prize in Physics, along with Russ Holtz, a fellow grad student of mine who sat in the desk next to me in the grad student office. Joe got into radio astronomy through ham radio, and he developed this protocol to listen to reliably to a radio signal that's 23 dB below the noise floor. And that will allow a university CubeSat with a 10-watt transmitter to speak to a university ground station without using the deep space network that NASA has. DSN is about $3,000 an hour, and it's very hard to get time on because it has a lot of demands for its time. And all of our software is written in Spark Ada. And so a little bit about our software: 5,991 lines of code, 4,000 lines of comments, 2,800 of Spark annotations, total 10,000 lines. And the examiner did, and this was Spark 2005, 42 verification conditions. They were eventually able to prove 98%. The initial try was 75%, and that showed us a lot of places where there were errors, which we took out, and got to all but 102 that were able to be proved. Again, probably with the newer versions, it could be totally proved automatically. And we suppressed all checks after running through Spark to prove no runtime errors. There was some C language, which was mostly a driver for SD cards. We did an interesting thing. You know, this is our first time doing a satellite, and when they tell you that the SD card is viable for 1 million read-write cycles, they're not being too conservative. The student wrote software that would write log files to the SD card. Instead of storing them for a while in memory and then writing them, he wrote every single thing to the card. And after about 1.5 million read writes, we started getting errors. We were not able to use that part of the software. So that's something to be aware of. And then comparing it, this is an older UK Ministry of Defense looking at the C-130J software, looking at errors per 1,000 lines of code on average. Some of the code was in C, some was ADA95, and some was in Spark ADA95. So the rate for C was 97, almost 1 in 10, ADA95, 25, and Spark 95 was 4. And in the Tokeneer project, which is Spark ADA 2005, the rate was 1/10 of that, or 0.4. Looking at the productivity from some studies of 38 lines of code per programmer day, about what our student achieved, very close to that, compared with 10 or 12 for C. And we're now using the newer version of Spark Ada 2014, and we will, as soon as availability, convert to 2022. And I did this comparison to talk to people who are not think they need to use Spark Ada because people already know C. And if a student knows how to program but doesn't know Spark Ada, it takes about 2 weeks to become productive, according to Peter Chapin working with our students. And with the productivity I mentioned before, with a program like ours, after 3 weeks, in our satellite, about 10,000 lines, excuse me. After 3 weeks, the Spark Ada programmer is caught up with the C programmer, and for the 10,000 line program, Spark Ada programmer will finish in 1.09 years with 4 errors, the C programmer in 3.33 years with 970 errors. Some examples where this technology would have helped: the Morris Science Laboratory has 3.5 million lines of C code. I'm not going to go over all the details on some of these slides. The slides will be available so people can read them in detail afterwards. Again, one would expect about 35,000 errors. As of 2014, they had corrected about 1,500. They didn't even get the software done in time. It was uploaded to the satellite, to the spacecraft on its way to Mars. And this thing wound up having an almost fatal error. If they didn't have a backup computer, it would have killed a $2.5 billion spacecraft. It had been the most expensive software error in history, but they were able to save it. Again, the Ariane 5 initial flight failure, many of you know about this. And this was the result of an overflow on a place where they had not had an exception handler. They did in some areas of the software. And this was at least a $500 million loss. And the Spark data would have prevented that. It would have found that there was no way to prove that you couldn't have the overflow. Boeing 787 generator control computer. There are 2 generators on each of the 2 engines, each with its own control computer programmed in Ada. The Airbus, on the other hand, their engines are controlled with Spark. The computer keeps count of power on time in centiseconds, which is used by track coaches and stopwatches. I don't know anyone else who uses centiseconds, in a 32-bit register. After 8 months elapses, the register overflows. Fortunately, the FAA was running a computer continuously and found this error. Boeing was not. And each computer goes into a safe mode in terms of the computer, but it shuts down the generator, resulting in a complete power failure, causing loss of control of the aircraft. So the FAA says to shut off the power before 8 months is the solution. And there's now a second reset problem that occurs in about 20 days, but only during takeoff or landing. So if it occurs during takeoff or landing, it'll kill you. If you're higher up, you'll have time to recover. This is, we were working on a project with Morehead State University, a 6U Deep Space CubeSat that was in fact launched last November on the Space Launch System. It would look something like this. This is one that I drew to created this image looking at an asteroid mission. It has these fold-out panels. That's what a more powerful panel, like 120-watt panels. These are made by CubeSat Kit, who made our structure and CPU board. This spacecraft would be using the Bit3 iodine propellant ion engine, which is used on the lunar ice cube with Morehead University. Just some information about that. Delta V is about 2,900 meters per second on that 6U CubeSat. So let's see, it would be 7, 8 kilogram spacecraft. Here's the thruster unit. It's, to give you an idea, it's a 10 centimeters in this direction and 20 in this direction, and about 15 in this direction. And this upper section here is a tank which holds 1.5 kilograms of solid iodine. These 2 are the gimbal motors that tilt it in the X and Y directions about 10 degrees. And this is another device very similar to the large one, but it's used for neutralizing the exhaust so you don't build up charge on the spacecraft. And this is just a quick, just look at it a couple of seconds of the thing starting up, the neutralizer first, and then the main thruster starts up. And then it tilts back and forth a little bit with the gimbals. See it move back and forth. That's all. Go for that one. And for the spiral thrusting, these are some of the things that were considered, looking at the axes and the kinds of computations that are done to see what's going on with the thruster. And the Deep Space Network, this is the ground station at Goldstone, California. There's one just west of Madrid and one just west of Canberra. And it's a 70-meter dish, 74 dBs of gain on X-band, and it's normally what is used for deep space communication. Give you an idea, the part that's moving up here is about 2,000 tons. This is the one version of the software, JT65, that Joe Taylor wrote, showing what's going on. When you operate the software, we've done some experiments with this, and I've listened to Moonbounce with this with one of our students, and some information about that. With a 3-meter dish at 9 gigahertz, you can reach Jupiter 4.45 astronomical units of distance between the Earth and the Sun. It's a very slow data rate, 72 bits in 48 seconds with another 378 with the forward error correcting. and it shows some of the statistics on the calculation. You can reliably listen to communication 23 dB below the noise floor, which is really amazing. And this is an example which could use this for deep space spacecraft. This is the Marco satellite that was sent out with a larger spacecraft landing on Mars, which relayed signals back. This is a fold-up passive phased array antenna, and this used X-band radio and was able to send signals back during the approach and landing, which is a very exciting part for a Mars lander. And so they had, for the first time, full capacity for listening to what was going on for the entire flight. This is showing this thing. It's just different size squares on the front. It's solid copper on the back, and by the different sizes, you have different phase changes bouncing off either the front or the back that allows this to simulate being a parabolic dish. And so it's pretty neat. It folds up. And then a typical university 3-meter ground station could be made from an old 3-meter satellite TV dish, which is what ours is. We have to mount it on a roof yet. We're not using this part of our ground station yet. And we have a grant to test that for CubeSat use, and we're using testing with 70 centimeters since the X-band transceivers are really expensive. And we're doing moon bounce. We will be doing moon bounce for the testing. We sort of got delayed with COVID, so we're going to get back to it fairly soon. And so our flight software is based on CubedOS, and so Peter Chapin and our students have worked on this, written in Spark. Again, I mentioned non-ITAR parts are on GitHub here. You can take a look at it. I'll show you examples of this, CubedOS and Merck, which is related. And the ITAR parts, as I mentioned, have to be gotten from us. And so again, we have verification goals and some of the testing that we've done. And so we use Jenkins for continuous integration. When we're working on it, it gets rebuilt every night, and it tests for to see that everything has gone well in the day's work. Collection of modules that pass messages to each other, and a collection of libraries called from the modules. It comes with a bunch of standard server modules and library facilities, and some small spacecraft flight software, and some of the various things that are available for it. And the sort of overall structure for the spacecraft that we were working with, Lunar Ice Cube, and a structure for the mailboxes. And again, I'm just going to go over this quickly. You can go back and look at these things. The slides will be available. And the mailboxes, have some message manager and some more stuff about that. I'm just going to go through quickly here. And then Merck is our second master's degree student, Sean Klink, wrote this. And this generates from the XDR descriptions, generates the file server programs. And then this is what is generated spec program and the generated body program, which is done by Merck. It's all from that. Now, there is a set of software that's available for small spacecraft that NASA's CFS, Core Flight Executive or Core Flight System. And it has similar architecture. It uses publish, subscribe, not point-to-point, so slight differences, and uses CCSDS as space packets for messages. It's written in C and therefore not verified. Now, NASA spent about $1.5 million trying to get rid of as many errors as possible. But we hope to offer CubedOS as a competing Spark platform for spacecraft software. And we're probably going to put together a bridge that will allow our software to work along with CFS. And so what was happening, so NASA's SLS, the Space Launch System, which launched the Orion capsule in November, and it was to carry 13 6U CubeSats, but 3 weren't ready on time, and they're working with C software. Even though SLS was at least 2 years late, they still didn't get the spacecraft software finished. We were working with Morehead State University on Lunar Ice Cube with CubedOS software. I think what happened, as a general physicist, I know a little bit about everything, and I'm able to spot errors in areas that the aerospace engineers missed. And I kept asking embarrassing questions that they didn't know the answer to, which they surely should have known on a $25 million spacecraft. And so they told us they're going to switch to CFS. And as Peter said, well, I think we've been thrown off a sinking ship. So it was launched. and it's now a $25 million piece of space junk. It doesn't work. And 10 satellites were launched of the 6U CubeSats on SLS. Only 3 were working after they were deployed. Again, Peter's book, which is available, most of you know about that, on Spark. And Vermont's first astronaut, hope to get ready. And some acknowledgments. So any questions?